welcome to this lecture on programmable logic devices in the course Digital System Design with PLDs and FPGAs. The last lecture we have seen the simple PLDs which has registers which allows one to implement data path and sequential circuit. Also we have seen some kind of fitting exercises because not all resources are there. How some techniques are used to fit the design optimally in those structures, and how like what is available today a versatile simple PLD like 22V10, we have seen that in detail. And as I said, mostly we have seen this because when we go to CPLD without much explanation, because we have learned all the basics and it is very easy to understand them, looking at this evolution of these simple PLDs to CPLD, that was the idea. So before getting on to the CPLDs and maybe some slight exercises, we will look at the last lecture slides quickly. So in the last lecture we have basically we have seen this structure. We said this can implement output by enabling this, disabling it can be input, and this product term can control it as output or IO, like a read bar can make it as a input, then read bar is high, it is output. And this can be used for cascading, like you have more than 7 product terms, then 7 can be implemented here, an inversion, second inversion, and that can be tapped here, you can implement, and so on. Also this can be used for cascading, can be used for feedback. We have seen you can build a cross coupled latch between these two sections using a NAND gate here, going to the NAND gate here and coming back to the NAND gate there, and of course with set and reset input. It's possible. So we have listed all that, all those facilities, and we have looked at the cascading scenario. Suppose we have 17 product terms. One way of doing is that you implement 7 here, take that 7 and put it to one AND gate, and then you are left with 6 product terms that you implement in 6 AND gates, then that makes it 13 and we need 4 more. So take this and put it here, and the last section will use 4 AND gates, and these two are disabled by retaining the connection or the fuses. But this will incur 1, 2 and 3 pass delay. So it's not a good idea. So the ideal thing will be to implement 7 here, 7 here, and you take both these 7 product term to a third one and use AND gate to cascade it, and use the rest 3 here. Okay. So that will make a kind of 2 pass, and you can go all the way in a 16L8 kind of device. Maximum you can use one last section with a 7 AND gate for cascading, and rest all section with the previous section with 7 AND gate. So 7 into 7 49 product terms can be implemented with 2 pass delay, and that's what we said. If you chain it you will get 8 pass with 49 product terms, but if you do a 2 pass like that, then you will get a same 49 product terms but it with a very minimal delay. That is how you cascade it. And we also have looked at the simple PLD like 16L8, 16R4, 16R8, and these are all with the registers, and which is not used, and 22V10 nowadays Atmel manufactures them. And basically the feature is that it is a very wide decoding. That means a product term can have, the AND gate can have 16 inputs and its complement, and this was used in chip select decoding. In a scenario like this you have a MUP, you have memory or peripheral, so you will connect the address bus. Maybe this has 20 address bus, say 12 are used for addressing the location, 8 are used for decoding. So one need to decode the 8 address line, higher address line, and that is where this PLDs were used, and this is the control and data. But nowadays what is happening is that many a time these are built into the SoC, and this is also built into the SoC, which kind of throw out the use of devices like these 16L8 and much more than that. Nowadays the peripherals are not directly mapped to the memory space, they have a serial port. Okay, so you have a serial clock and the IO data in and out, and this support the support is elaborate, addressing is through the data frame, and you can have multiple slaves, multiple masters, all that. So this kind of removed the need for the simple PLDs. That is why it is not used very much. And for understanding, we have looked at the 16R4. It is nothing but 16L8 structures, but at the output you have some 4 flip flops, and so you have a combination section and registered section, a common clock and an output enable. Important thing is that the Q bar is fed back into this array. So essentially what can be done is that you can have a state flip flops, a next state logic with all the inputs and the present state fed back. So you can implement the counters, okay, with the next state logic here, and this is the state flip flop, and you can even implement a state machine, because this feedback the present state can be decoded in this array and generate the Moore kind of output combined with the inputs, because everything is available here. Combined with input you can make it melee output. Okay, so that is how the data path, and if you have a register, combination circuit register, even that can be done. You can start with inputs going to a register, that output is kind of computed with a combination logic, that output can go to another flip flop, and you can imagine parallel kind of data within the constraint. Suppose you have a device like 16R8, then that is not shown here, but then you have all the registers, then you can have maybe little more data bus width in that case, and we have seen how this is mapped, data path, combinational data path. So you start with the source register with inputs coming in, because the inputs are available to every kind of section, then that present state is fed back, and then you have a next state the combination logic, the output go to the destination register. And if you have a state machine, you have the flip flop, input and the present state comes here, and the output and the present state goes to output logic. So exactly same, you have the inputs, you have the state flip flop, the feedback is here, so input and the present state is combined in a next state logic and goes to the state flip flop. The present state and input is again decoded to produce the output. So it's it looks like this structure itself is converted into this form, and it is very nicely, so it's a nice kind of architecture wherein the sequential circuits can be easily implemented in a PAL, and whether you look at this way or this way, it does not matter. Maybe this is ideal because you have a kind of say if you view like that, you have the next state logic and output logic here, all the inputs and the present state is coming, so this form the next state logic and rest of the part forms the output logic. Okay, so that is how the sequential circuit and data path maps into this. And one thing I said that suppose you are implementing kind of say 2 product terms here, okay, say take an example, X is AB bar and CD, and that X is implemented here, and Y is nothing but this X plus 2 other product terms. So one way of implementing is that X you implement 2 product terms, Y you implement the feedback, maybe X you implement here, that X you combine in one product term and implement the next 2 product terms here, but then the delay will be 2 pass. So it is easy if we can replicate that product terms here, substitute. Okay, so that is what is done here. So instead of using a node here, already implemented node, we substitute this product term and straight away implement that because the product terms are available. Okay. So this is called virtual substitution, but this can go wrong like in the case of an XOR, because in this symbol structures there is no XOR, and A XOR B is AB bar or A bar B, and when you take 3 XOR then you will end up with 4 product terms, n XOR 2 raised to n minus 1 product terms. And so if it goes on expanding, then suppose you have say 10 XOR gate, then you will end up with 2 raised to 9, which is 5 total product terms, which may not be available in a simple PLD. So when you implement XOR kind of circuit, priority encoder, the arithmetic circuit where XOR is there, if substitution is kind of implemented, then there is a problem, and this is like it is better to implement kind of don't do the substitution, like you implement A XOR B, then in the next section you XOR with the C, because you implement 2 product terms in one and bring it here and do the XOR another 2 product terms here, then keep on expanding. So that is why that the substitution may have to be turned off to avoid this kind of cases. And the last we have seen is the 22V10, which combines the utility of symbol combinational device like 16L8 and 16R8, wherein you have something called a macro cell, which is nothing but flip flops with bypass, so that this section can be used along with the register or directly. Okay. And you have the clock, common clock to the flip flop, and the feedback can be from internally if it is the flip flop is used. If it is bypassed, then the feedback is from here. Okay. And if we are using all section like combinational kind of logic, then this clock is not required, that is used as input. The variable product terms, first section has 8, 10, 12, 14, 16, and then it is mirrored down. There is a product term controlling the asynchronous reset and another product term which is controlling the synchronous preset. So quite versatile, and we have seen what is inside this. So basically AND OR, then there is a register, but there is a mux wherein you can use the combinational output directly or the registered output, and you can use the combinational or its complement Q or Q bar, and this allows you to apply the De Morgan's theorem and optimize the product term. Suppose you are using a section with 8 product terms and you implement Y. So normally say if you use Y, then you implement Y here, go through this inverter, you get it. But suppose that has more than 8 product terms, you implement Y bar here, Y bar here, it may reduce to say less than 8, and you can implement it here, then you invert here. So this section allows a product term optimization, and this is the feedback mux choosing the Q bar or the input, and this is the product term which is controlling the tri-state enable. So this combines, this can act as a 16L8 or 16R8, that kind of flexibility is there, and this is available now, this can be used. So the features we have seen, you have variable product terms, asynchronous reset, synchronous preset, you can use it as combinational or registered output, product term optimization, and an example we have seen, like there is a Y with 4 product terms, so you do the De Morgan's theorem, then minimize it, you end up with 2 product terms. And these are the kind of delays. You have propagation delay when it is used as combinational kind of section, this is the delay of the tri-state gate. Then you have the flip flop with setup and hold time, the TCQ, we have discussed this, and the kind of reset delay with the asynchronous reset and all that. Okay. And then with or without feedback we can kind of, you can work out, suppose you have like you have a combination section with feedback, then you have to kind of add all that delay and with feedback you will have some extra delay because there is a mux and that will be added to that. So that is the timing of the PAL22V10. So I am putting a kind of question. This is an exercise kind of thing. Question is that is it possible to implement an 8-bit odd parity generator in a PLD22V10. That means parity generator has 8 data inputs and 1 parity output. So you know that this parity generator is nothing but you have suppose I1 XOR I2 XOR I3 like that it goes, okay. So first thing when you try to address that there are two things to check. You have a 22V10, okay, that the 22V10 internal. So you have kind of 12 inputs, dedicated input, 10 dedicated output. We have to check whether input and outputs are sufficient to implement this function. And second thing to look is that whether the number of product terms are enough, okay. So let us check that and the IO requirement is that number of inputs is 8 because it is an 8-bit parity generator, but we have 12 dedicated outputs. So 8 is okay. Now sorry, this is 8 less than, so in a hurry I put it greater. So 8 less than 12, so you have that is sufficient, and number of output is 1 less than 10 output of 22V10. This should be enough. So I apologize, this you treat it as less than, okay. And we don't have any XOR gate in 22V10, neither in the combinational AND OR section nor in the macro cell anywhere, okay, because there could be some PLDs where there is an XOR gate at the output. We will see that in CPLDs, okay. So there is no XOR, so we have to the tool has to kind of expand this in terms of AND OR gates, okay. Now we assume, like for this we assume that we are implementing the substitution, we are expanding it, okay. That is what we assume, that we are assuming that it is expanded, okay, substituted. So XOR of n variable, that means we are not implementing intermediate nodes, okay, we are expanding it. So maybe that assumption one can write here. So for n variables we have seen just in the previous lecture there are 2 raised to n minus 1 product terms. So that is why if the odd number of input bits are 1 then the output is 1. So from there you can understand that. So for 8-bit inputs we need 128 product terms because 2 raised to 7 product terms are there. But if you look at the total product terms available in a 22V10 PLD is 8 plus 8 into 2 plus 10 into 2, 12 into 2, 14 into 2, 16 into 2, okay, and that we will end up with 120 product terms, but we have 128 product terms. Much more than that we have to cascade, okay, and we have 10 section. So one we use for cascading, then we have 9 section for cascading. So we have to use a section with 10 product terms for cascading. So we are left with 120 minus 10 product terms. So we have only 110 product terms, hence these resources are not enough, okay. So it cannot be fitted, okay. So provided, I mean we are assuming that we are expanding, we are keeping the delay minimal, we are not kind of implementing the intermediate node. It's possible that you implement an XOR gate then cascade it to the next XOR gate, cascade it to the next XOR gate, then it will be possible to implement, but then it will incur a lot of delays, okay. So you can approach various other ways, you can think of a tree implementation, wherein you can start with some 4 XOR gate, 2 input XOR gates, then it goes to the kind of a logarithmic reduction can be applied, then it is possible to implement. But I am discussing the case where normally the tools kind of substitute, expand it. In that case it will not be able to fit in, and that is a case with minimal delay. But a cascading, some kind of chain cascading or kind of logarithmic kind of cascading, binary kind of 8421, that kind of cascading will work with this 22V10 fitting. Maybe you have to kind of manually little bit give attributes to do that. So that is I mean, one advantage of knowing the architecture and the tool is that you can quickly work out whether something fits in, and that I want to highlight, because if you have no idea of the architecture you will not be able to exploit these kind of situation. Okay. So if you know that using the tool attributes, using some kind of coding techniques, you can get out of the kind of bad situation to implement something, and which many times people ignore, and that is true when we go to CPLD or FPGA to know the architecture. And we also know that given something, whether it really fits in, whether the device is able to kind of implement that thing and the resources are enough, you can do a rough kind of estimate wherein whether the given circuit, given logic fits into the to the device. So that is possible. So that is the advantage of learning the architecture, learning how the circuit maps into that. And I have taught you, when we discuss VHDL, we know given a VHDL code how an RTL circuit or the equivalent logic circuit can be inferred. So if you apply that knowledge, and somebody has given a VHDL code, so I am sure you can work out the logic which that the tool synthesizes, and you check in the target device whether it can fit in. All this can be kind of even in a complex design, when you break into pieces you can estimate it. It does not take much time, and you can rightly choose the devices, and something goes wrong, like if like you try to fit something in a 22V10 and it says that it cannot fit. So looking at the reports you can make out what is going wrong, maybe and implementing it as an internal node or using some different cascade structure, you can implement whole thing with minimal delay. All this can be done. It is a very simple kind of device, simple cases, but having that knowledge will enable you to do many optimization which a novice or those who are just working with the tool with some kind of Verilog or VHDL will not be able to do it. Okay. So applications of the SPLD is that you can implement some glue logic. Glue means that you already have chips for say a microprocessor, memory, some embedded system, but some random logic, some simple logic you need to implement for whatever reason. Such things can be combined in an SPLD. Now it need not be related. Maybe while interfacing one chip you need some kind of translation of the bus protocol or some small thing, all that can be implemented. Many things together can be implemented because there are 22 IOs and 10 outputs, so many things can be done. Okay. And it definitely you can implement counters, small state machine. The disadvantage is that such kind of wide decoding, the AND gates with lot of inputs are not required in many cases, and the number of flip flops are less. You know that you take this 22V10, there are 10 flip flops, and practically you cannot do much with the 10 flip flops. You cannot have any kind of memory implemented here. Suppose you need a shadow register, that cannot be implemented. So because of the lack of registers, though the logic is quite the logic section gives you a lot of product terms, but lack of registers limit the use of these devices. Okay. So that is about the applications of simple PLD like 22V10. Then let us look at the programming technology. That means that say 22V10 like devices can be fuse programmable, but nowadays it is not used, of not very of any kind of practical interest. Earlier there were fuses I have shown in the initial slide, a fuse and passing a large current and blowing it. Then there were EEPROMs, again is not very much used. These were kind of devices which can be electrically programmed, and once you program it, to erase it you expose the silicon die through a glass window to the UV light, and some 5 to 10 minutes of exposure will kind of remove the programming. Okay. Once again this was quite famous maybe 20 years back or 15 years back, wherein all the memories, the EEPROM will have a window and you program it, and when you want to erase it you expose it to UV light for some time, like you cook the device, then it gets erased, and not very much used at all, not used at all now, not required. But then we will have a look at those transistors just for the learning purpose, because the next technology is kind of related to it. Okay. It is a variation on that. So the another technology used is EEPROM, where it is electrically programmable, electrically erasable. Okay. Here it is electrically programmable, UV erasable, but here it is electrically programmable, electrically erasable. Okay. Basically, and there is flash transistor which is kind of similar. Okay. It is not much of a difference, construction wise it is different, and there are a number of erase cycles is more in flash than the EEPROM. Number of times you can reprogram is more in flash, but then kind of the data stability will be more in EEPROM, where there is this is less susceptible to noise and all that. But then again this bit historic, nowadays everybody use flash. So if you ask me, the current technology is the flash. All these are of kind of little bit historical interest, but nice to look at it, because the way evolution has happened will teach you something. So we will look at those the fuse we have seen, these three we will look at it. Okay. So this is the EEPROM transistor. This transistor is used to construct the AND gate and the OR gates. Okay. And as I mentioned, it is a wired AND gate, it is a wired OR gate. Okay. So we will see how this enables one to implement that wired structure. So I think you are familiar with the CMOS transistors. So this shows an N channel or NMOS transistor where there is a substrate is P type. So normally you will have a big substrate and you will have an P well, in that there will be N channel, and normal transistors will have a insulator here, silicon oxide. Then there will be a gate, polysilicon or copper gate on top of it, and normal case there will be only one gate, and what you do is that source you ground, drain you give a supply, say 3 volt or 5 volt, then you apply 5 volt here. Because of this electrical field, the electrons will come here and N channel is formed, a conduction happens. Okay. Now in this EEPROM transistor there is silicon oxide, there is a gate which is a polysilicon which is floating, which is not connected to anything. Then there is silicon oxide, there is a normal gate, control gate. So in the normal case it will act as an N transistor. You ground the source, you apply the drain voltage, you give a gate voltage which is above the threshold voltage. Because of the electrical field which is to the positive side, electrons come here, form a channel, it conducts. Okay. Now this floating gate allows you to completely turn it off. Okay. When you turn it off, it acts like blowing the fuse. Okay, that is a basic idea. Okay, we will see that, but why we turn it off is that this control voltage will have no effect on the conduction. Okay, that is how we kind of blow the fuse. Okay, so what is done is that you ground the source and you apply the positive voltage to the drain, and a brief positive pulse is given here, like say the supply voltage is 5 volt, maybe you give a 6 volt or 8 volt pulse for a short duration. Because the electric field is high and this layer is very thin, it is only very kind of, it depends on the technology. Okay, and this is shows that 150 angstrom, but it depends on the current device technology. Compared to the normal silicon oxide thickness, it is less. Okay, and what happens is that because of that field, electrons travelling to the drain will tunnel through this thin insulating layer and get trapped here. Okay, because it is a conductor. Okay, it gets trapped here and then you stop it, and what happens is that because some electrons are sitting here, now to form a channel here you need to apply more voltage here. So if you apply a 5 volt the gate voltage, channel wouldn't be formed and there is no conduction. So it is like a transistor which in the absence of this captured charge, it acts like a normal N transistor, and when you program it to be off by capturing the electrons, then it does not conduct even if you apply. So it is like blowing the fuse. Now we use this transistor to build a wired AND or wired OR structure. That is how it is programmed off. Okay. So suppose you want, say, a particular input does not affect, then you just program it off, and we will see that structure. And to erase it, there is no easy way. In the case of EEPROM transistor, as I said, there is a like these silicon die is in a chip, there will be a window on top of it and you expose it to UV. These electrons, because of the UV radiation, will get enough energy and tunnel back and get out. That is how it is erased. Okay. So we will see how a wired structure is formed. Okay. So now take this AND gate. So what we are trying to build is an AND gate, okay, with say 32 inputs, okay, or some kind of some number of inputs, and so many AND gates goes to an OR gate. Okay. Now these AND gates are built using these transistors, okay, and it is a wired structure, we will see that. So this is how it is formed. So this shows assume that this line is an AND gate, okay, this line is another AND gate. Okay. So if there are 32 inputs, then there will be 32 vertical lines as shown in the picture, and at the between those vertical lines are connected to the gate of this EEPROM transistor. The drain is connected to this common line, the source is grounded. Okay, all NMOS transistors with floating gate, and this line is pulled up through a transistor, through a resistor or a transistor acting as a resistor. You can have an NMOS transistor with the gate connected to the VDD can act as a resistor. So don't think that the resistor is implemented as a passive, it can be an active circuit, because in a single die you can implement transistors easily than again bringing in the passive elements. Okay. Now suppose, and these vertical lines are connected to the input, suppose this is connected to I1, I1 bar, I2, I2 bar and so on. Now if you do not program it off, you see when this line is high, any of the vertical line is high, this transistor will be on and this line is pulled low. So the logic is that if you retain some connection, if you do not program it off, if that line is high the output is 0, okay. So if input is high, any one of the input is high, output is 0, it is a wired NOR, okay. So it is a NOR circuit, okay. So NOR is like there is a OR gate and a NOR gate, okay. So these bubbles are not there, but what we want is an AND gate, okay. So we know that again we have studied the gates and function, but if you invert the A and B, okay, then it will become an AND gate automatically. So this structure, if you give one input directly, it will implement a wired NOR structure, because any input is high, this line is 0, so that is a NOR gate. But if you invert the input, instead of I1 you connect I1 bar, then instead of I2 you connect I2 bar, then automatically it implements the AND function, wired AND function, okay. So that is what is shown. Normally it is a NOR gate, but you invert the inputs, then you will get an AND gate as far as the active high circuit is concerned, and that is nothing but Y bar is A bar or B bar, okay, which is nothing but Y is it is applying the De Morgan theorem. If you invert, then you get the AND gate, okay. Now that is very easy to do in a PLD, because you see that all the inputs are inverted, both input and the complement of the input is there. So how it works is that, suppose you connect A, this line act as A bar and this inverted line act as A, okay. So you want to program A to this this AND gate, then what you do is that you retain the connection of A bar, and you blow the, you do not put off the connection for A. So instead of where you want to use A, use A bar, where you want to use A bar, use A, and since both are available, it is a matter of swapping the position of the programming, okay. So that is what I have shown. For I1, the I1 bar is used, I2 bar is used. So that is very simple. For a like an AND gate with 32 inputs, you need 32 EEPROM transistors with a single line with a pull up transistor, and similarly you replicate that structure. You have kind of 7 product terms, then 32 into 7, which all goes to an wired OR gate, and the same structure is there, it is a wired NOR gate. So you put kind of here you have say 7 input OR gate. So same thing, these 7s are going to 7 these kind of transistor with a single line pulled up, and you put an inverter you can put with NMOS and PMOS or 2 NMOS, then you get an inverter. So this wired OR is nothing but a similar wired NOR with inverter. So you see how this is programmed using the transistors alone. It is very easy. That is how it is implemented in a PLD or CPLD and things like that. And so wired NOR with input using complements, transistors are EEPROM. So when programmed there is no connection, when you program it off there is no connection. And the fixed OR, that is a programmable AND, fixed OR is nothing but wired NOR followed by an inverter. Normal N type transistors are used, so it is very easy to implement. It doesn't, you do not have to worry whether how to kind of implement the 32 input AND gates. It is not very complicated logic in terms of transistors, okay, because the wired versions are implemented. And let us look at the flash or EEPROM transistors. The construction is similar, but the gap between the floating gate and these channels are low, okay. And you can also see that like if you see the construction will be little different. It kind of little more extend over the channels, this source and drain. Now what happens is that similar operation, you just ground the source, apply the drain voltage, and you give a programming pulse of little higher voltage to this gate. So these electrons, there is a field from drain to source, there is a field from source to drain, electrical field from the substrate to towards the gate, and because of higher voltage the electron get trapped here. So it is programmed off, but you want to erase that. What you do, you do not have to expose it to UV, you do the opposite. Okay, you ground the gate, you ground let it be floating, and you apply a higher programming voltage to the source, then these electrons tunnel back and you can electrically erasable. So in the circuit, the advantage with this transistor is that it like you kind of you can electrically program it and you can electrically erase it. It is very fast than exposing it to UV. The flash is kind of flash and EEPROM, the construction wise little difference is there, but only one problem is that when you program it off, this because of the construction, even if the gate voltage is less than the threshold voltage, it conducts. Okay, so this can only be used kind of cut it off, and you need a normal transistor in series for really controlling the wired, implementing the wired NOR function. So this is how when you use flash or EEPROM, use a normal N transistor for forming the wired NOR structure or wired AND structure with appropriate inversion, and you in series you connect this kind of the flash cell or the EEPROM cell to cut it off. When you do not want one input to be connected to this AND gate, then that you program it off. That is how the flash or EEPROM structure is used. So and the programming interface, the programming standard is it uses JEDEC file, it is a company's name, it is a standard ASCII file, fuse pattern will be 0 and 1, where there is connection it will be 0, where there is no connection it will be 1, and the normal pin of the PLD is used for programming. So there are the address, basically you have to address this fuse location or the transistor location to program it. So there is an address line, data line, read write line, and the program pin. So how is a higher programming pulse is applied to this program pin, then it gets in the program mode, then you give address, data, read write signal in the appropriate kind of with timing, it gets programmed. Then you can use it as a normal device with IOs being used as user IO. Okay, and the program you put it in the programmer, you can erase it and reuse it. So that is the all about the SPLD. So what we have seen today is in the just the previous part is that we have looked at the various one example of fitting, and we have taken a kind of a parity, odd parity generator, and we have assumed that that we are kind of expanding it in terms of product terms than implementing it in a node, and we have found that 8-bit odd parity generator with expansion cannot be implemented in a 22V10, but with internal node kind of one-to-one picture of a chain of 8 2 input XOR gates, or you can cascade 4 2 1 of 2 input XOR gates, all that can be implemented. So that gives you kind of freedom, and as I said, that kind of give you an idea how to know the architecture of a device and how to map from even from a VHDL code down to the level of fitting. You can after some practice you can even start kind of working this in the mind, even in a complex circuit by part. You can take a paper and start working out whether how many flip flops are required, how many sections are required, how much delay it will incur, and all that can be calculated. You can estimate, a rough estimate can be worked out, without blindly going to the tool and coding, playing with the tool and all that. It's all possible, but you can do that yourself, that's the advantage. Then we have seen the programming technology, the fuse we have seen the EEPROM transistors, how a floating gate allows the transistors to be cut off. That means you can program off the transistor, and the same transistor is used to implement a wired AND gate and wired OR gate. Essentially it is a wired NOR gate. For AND gate we kind of invert the inputs, and it's very easy in PLD because all the inputs and their complements are available. So wherever the fuse for or programming for A is done in the A bar section, and for A bar you do in the A section, that's all the difference. So appropriately tools take care of programming it, and we have looked at, and that the problem with the EEPROM is that you have to UV raise it. It takes time. More than that, you have to take the expose the device. After some time the device will become unusable, and EEPROM and flash allows you to electrically program and electrically raise it, and we have seen that structure also, but it conducts normally. So we put a normal transistor to form wired AND gate and wired OR gate and put this in series to program it off, and that's the basic idea. And simple PLD applications we have seen, it is used for glue logic, you can implement counters and FSM, and it can be used for very small logic, but the lack of flip flops doesn't enable it to be used in complex application. So that is the simple PLD. With this knowledge we can quickly grasp the complex PLD, and that's my idea. So let us look at the complex PLDs. Okay. Now the first thing to look at is that you see that when you say complex PLD, say you take this 22V10 structure. Okay. Already we have a section with 8 product terms, 10 product terms, 12 product terms, 14 and 16 product terms, and as I said most Boolean function doesn't need all these kind of product terms, and the product terms are very wide. This can implement up to 20 variables and its complement. It's quite complex. Now when you say complex PLD, we don't need to scale this up. It doesn't mean that we make a say 100 V50 or something like that. It makes no sense. You have 100 dedicated inputs with maybe say 300 vertical lines and some 25 product terms with 100 section. It makes no sense. It will be wasted. There is no use. Okay. But we already know that this structure can implement counters, FSM, and it can implement the combination logic when you bypass it. So it makes sense to have this 22V10 like structures as a building block, put multiple of them together and somehow interconnect them. That means that there are a set of IO pins, there are a set of 22V10 like structures. You should be able to connect the inputs to here or some other section, take the output of this section to the input of the next section. So the idea is that maybe in one section you implement a counter and you decode it, and that goes to an FSM in another section through a kind of IO switch, and that section goes to some the FSM output goes to control some other thing and so on. So instead of a big PLD, the CPLD is, we can say, is not a big PLD, it's a kind of hierarchical PLD. So it's not like you have multiple SPLD sections interconnected. The requirement is that output of any block, a SPLD block, should be able to go to one or more input of other blocks to cascade, and any input signal should be able to go to the one or more input block. Okay. So basically you have in a complex PLD or CPLD, it's a hierarchical PLD. So you have simple PLD sections interconnected by a switch, that is called CPLD, and you have a product term array, that means basically AND gates, basically product term array, and product term allocator or a distributor. That means these product terms are not permanently connected to an OR gate. Depending on your need, it can be connected to an OR gate, it can be connected to an XOR gate, because we have seen the simple PLD kind of lack an XOR gate, and that is a major disadvantage, because when you try to implement expand XOR gate in terms of product terms, it goes out of hand. So it makes sense to have dedicated XOR gate for parity, for product term optimization, for arithmetic circuit, all that it is useful. So XOR gate, and so this product term allocator allows you to use AND gate to an OR gate to one of the input of XOR gate, or there are macro cell wherein flip flops are there. Maybe one AND gate can reset the flip flop, one AND gate can set the flip flop depending on your need. So this allocator, we can say it's a small switch which allocates this product term to various need, whether it can be used directly outside to the OR gate, XOR gate, or the flip flop controller, so that nothing is wasted. Okay. So if you permanently connect some AND gates to an OR gate, say there are 5 AND gates, it is connected to an OR gate, but we only need one AND gate, but we could have used that another AND gates to the input of an XOR gate. Okay. So this allows flexibility, this allocator or a distributor, nothing but a switch which connect the output of AND gates to the various inputs of the OR gate, XOR gate, flip flops and things like that. And the macro cell is like a 22V10 which has a flip flop with bypass and so on, and the IO cell is nothing but IO pin with the tri-state gate with a input, so it can be used as output, input, IO, can be used for feedback, and there is a programmable interconnect which interconnect this simple PLD section. So huge switch which take the output of one section to the input of other sections, any input signal can be taken to the input of any sections and so on. So that is the programmable interconnect. So basically any CPLD you look at it, there will be multiple simple PLD section, a interconnect which interconnects the IO pins and the PLD section. Within this PLD section you have a product term array, basically AND gates, a product term allocator which allocates the AND gates to the various combinational and registers. You have registers with feedback, then the IO pins, that constitutes a CPLD, and we will see some example of the commercial CPLD available today and see how this is kind of this architecture is implemented. Okay. So basically as I said, these are kind of simple PLD section interconnected, and if you look at the Xilinx manufacturer, then you have 2 series of devices, XC9500XL. Okay. This is a CPLD which was there from very beginning, and the Cool Runner 2 series of family. The architecture is similar, only thing is that as the name suggests, it has very low power dissipation, that is why it is called Cool Runner. And when it comes to Altera, they have a series called Max 3000, A, Max 7000, and there are very different variations, Max 2, Max 5, all that. So there is at least 4 families, and Atmel has ATF15 series with some numbers. Lattice Semiconductor has ISP Mac 4000 ZE family. So you have quite a bit of choices between Xilinx, Altera, Atmel and Lattice Semiconductor, and if you look at the architecture it is all kind of similar architecture. At least I know that the Xilinx architecture and the Altera architecture are somewhat kind of similar. So for this kind of discussion I will take the MAX 7000 as an example to show you the architecture which can be easily applicable to the Xilinx architecture. There is no much difference at all. If you look at the data sheet you would find that it's quite similar, and whatever I am discussing for this can be applied to this both of these. Okay. So maybe that we do in the next lecture because we are kind of coming to the close of the this lecture. So the complex PLD is not a big simple PLD because it makes no sense, because simple PLDs already has a lot of product terms which support a lot of inputs, and what we need is that, and we have seen that counters, state machine, random logic can be implemented. So when there is a medium kind of or low complexity some particular circuit, we will discuss that what kind of applications can be used, then it makes sense to have multiple simple PLD section interconnected, and we have seen what kind of interconnection. The IO pin should go to the input of any section, output of any section should go to any of the input of the other sections. Okay, so that we can kind of interconnect this section to implement some reasonable logic. So it has a PLD section, multiple PLD sections, interconnect array, a product term array which is composed of AND gates, product term allocator which allocates the AND gates to the OR gate, XOR gates or flip flops, a macro cell which consists of various the XOR gates, the OR gates, the flip flops, the bypass and so on, which allow with a lot of more control, more flexibility than a CPLD. That means you are able to connect a global clock or a product term clock, global reset or a product term reset. So you have more flexibility in CPLD than in a simple PLD. So we will, and we have seen some kind of available products from the Xilinx, Altera, Atmel and Lattice Semiconductors, and as I said in the next lecture we will take an example of MAX 7000 series of Altera. We will see the architecture, we will see some kind of code, how it maps into this device and so on, and then we will we will see the application where it can be used, and then we will wind up the PLD part and will move on to the FPGA, and we will find what is the difference between the PLDs and FPGAs and so on. So I urge you to go through this portion for yourself. You imagine some kind of logic, work out how it fits in. Maybe I have told an example of a priority circuit, maybe you can think of a counter, how it fits in, what is the basic Boolean equation, how it fits in a PLD like 22V10, what is the delay and so on. So I wish you all the best and thank you.